So today, in this lecture, we'll discuss more about how to simplify network of resistors if they're connected in series or if they're connected in parallel. Okay. So let's first start with series resistors and volt division, and in the next part we'll see about parallel connection. So resistors can be connected in series or in parallel, or in a delta connection, in a pi connection. There are different ways that we connect resistors. So if two resistors are connected in series, that means just like this, they have to be connected back to back, and they will have one common or junction point. So let me just clear these all drawings. Okay, if two resistors are connected in series, let's say R1 and R2. So let's say this is a resistor R1 and this is a resistor R2. Now, if these two resistors are connected in series, it means they have one common point. So we'll just only connect one terminal from each resistor or from each component. If you see, the other terminals are not connected, so they don't touch. So we only connect one terminal. That's one thing. And the other thing is we do not have any other component between these two resistors. So if, for instance, if I have another resistor, let's say R3, which is connected to this common point of the two resistors, then R1 and R2 are no longer connected in series. So in order to say that two resistors are connected in series, there should not be any other component between these two. Nothing. Only these two. So we say now R1 and R2 are connected in series. So there are two things. First one is we have the two components has to be connected at one junction or at one node. And the second thing is there should be nothing between these two resistors. If we connect any other component between these two, well, then these two are not connected in series. We'll see later on. We'll say a couple of things when we connect other component in series with the two. Now, if instead of putting it that way, if I have, let's say, now I have R1. Sorry, let's say I have R2 and I have R1 here. This is one. Let's say I have R1 and R2. Now they're not connected to each other. Now let me just bring one resistor, R3. Now let me say that R3 is connected to R1. It's not connected to R2, but it's connected to R1. So according to our definition, right, we say that R1 and R2 in the top figure here, we say that R1 and R2 these two are connected in series. So according to that, here we can see that R1 and R3 are connected in series. Why? Because they have only one junction, one node between these two, and we don't have any other component between these two. So these two are definitely connected in series. Okay. Now, let me say that now R3, let me say that is connected now to R2. And on the other side, now forget about the right side, and let's go to the right hand, to the right side. Now here, basically, according to our definition, we say R1 and R2 are in series. Here also, R2 and R3 are connected in series because we only have one junction, right? We don't have any other component between R2 and R3. So therefore, we can see that R2, because we only have one junction, so R2 and R3 are connected in series. So these two are connected in series. And R3 and R1 are connected in series. So therefore, R1, R2, R3, all these are connected in series. So we can generalize that. All the three resistors are connected in series. Connected in series. So in order to see or to decide whether the components are connected in series or not, we have to see if they're connected at one point and if there's nothing between these two. So if multiple resistors are connected this way, we can generalize that all these resistors are connected in series. Now, if resistors are connected in series, then they have the same current. Let me just let me go back in. Okay. So let me just go back to the first. Now R1 and R2 are connected in series. Let's say the current through R1 is I. If R1 and R2 are connected in series, the same current flows through the second component. So we have the same current. So if two resistors are connected in series, both will have the same current. So the current will be the same. So the current through R1 is I, the current through R2 is also I. So they both have the same current. So if I want to find, so the current, let me just say, okay. So current will be the same. The current will be the same across through each component. So they do have the same current. But what about the voltage? But if you see the voltage, unless R1 is equal to R2, the voltage does not necessarily be the same. So the voltage across R1 or across this part, the voltage across R1 is I times R1. And the voltage across the second component is I times R2. Now, if R1 equals to R2, then the voltage across each component will be the same. But if the resistance value is different, and so does the voltage. So using the same principle, if you go to the second connection, R1, R2, R3 are connected in series. So all these three are connected in series. So if all, let me just clear this. So since all these three resistors are connected in series, so what we have is, if I is the current that goes through R2, then the same current goes through R3, and the same current goes through R1. So as long as they are connected in series, they have the same current. So let's say if I want to find the voltage across R1, so the voltage across R1 will be I times R1. The voltage across R2 will be I times R2. And the voltage across R3 will be I times R3. So the voltage across each component can be determined using this way. So unless all the components have the same resistance or they have identical values, then the voltages does not necessarily be the same. So it may not be, it won't be the same. So all components or all resistors, if they're connected in series, they have the same current, but they may not have the same voltage, not necessarily. So this is one special thing we see for resistors. I think. Let me just. Okay. Let's say the source voltage is Vs. This is R1 and this is R2. Let me assume that the current that goes through the circuit is I. Now, if you write KVL, right? If I write KVL for these circuits, let me say, it's just to show you how we get a voltage division rule. So if I write a KVL for this loop, if I start from the voltage source, right? If I go this way. So we're going from minus to plus, so it is minus Vs. Then we have a voltage drop, this will be plus, and this is minus, always, if the current is going that way for a resistor. So I will have plus the voltage across this one. The voltage is I times R1, so I times R1. And again, this will be plus, minus. The current goes through the resistor, so the voltage drop across this one is I times R2. It will be 0. So this will be Vs is equal to I is common to both R1 plus R2, right? If you take Vs to the other side. And if you solve for the current, I will be Vs over R1 plus R2. So this way we can determine the current through the circuit. So if you have two resistors and a voltage source, and if you're asked to find for the current through the circuit, I equal to Vs over R1 plus R2. Well, good. Now the current, since the current is the same, and then once we determine I, then that will be the current through each component. Now our goal is, let's say our goal is to determine the voltage across R1. Now the voltage across R1 is, the current is I, the resistance is R1, as we said earlier. This is I times R1. But we have the expression for I. So I is Vs over R1 plus R2 times R1. So if we rearrange this will be R1 over R1 plus R2 times Vs. So that's why we say, if we want to define the voltage across each component, we don't need to solve for the current. We can use this expression directly. So the voltage across R1 is R1 over R1 plus R2 times Vs. Similarly, if we use the same step, the voltage across R2, or the second component, will be R2 over R1 plus R2 times Vs. So this is defined as, a voltage division rule. So the voltage across any component can be determined using this equation, as long as those components or those resistors are connected in series. So this works, or this is true, if and only if the resistors are connected in series. So if they're connected in series, then we can use this expression. If they are not, then these two equations will not be valid. If we have more components, now what if I have multiple components? Let's say I have 1, 2, 3, 4, 5. Let's say I have 5 resistors, and I want to find the voltage across each component. Let's say this is R1, this is R2, this is R3, R4, R5. Let's say this is plus, minus, this is the source voltage. Now in this case, if I want to find the voltage across R1, it will be, since I want to solve for R1, so it should be, R1 should be on the top, divided by the sum of all resistors in the circuit, R1 plus R2 plus R3 plus R4 plus R5 times source voltage Vs. If I want to find the voltage across the I's component, or Ri, I can be 2, 3, 4, or 5. This will be Ri, or the I's component, divided by all resistors, the sum of all resistors. And then we multiply that with Vs. So this way, if we have 100 resistors, we use the same format. The only thing that changes is the denominator. Now, the sum of the resistors that we have in the denominator is defined as the total resistance of the circuit. So this is the total resistance. So this is the total resistance of the circuit, the total resistance, or the equivalent resistance. So this is R equivalent. So this is the total resistance, or the equivalent resistance of the network. So if I have 5 resistors, and if all of them are connected in series, the total resistance, or the equivalent resistance, will be simply the sum of their resistance. Now, if I had, let's say, R6, R7, R8, like this, if I had 8 resistors connected in series, the only thing that changes is here I will have plus R6, plus R7, plus R8. Here also, what I will have is plus R6, plus R7, plus R8. So that's why if we generalize the voltage division rule, this is simply Ri, the voltage across the I component is Ri divided by the equivalent resistance, or the total resistance, times Vs. So this is the generalized voltage division rule. So this is voltage division rule. So the voltage division rule. So Ri is the I's component, the resistance of the I's component, and Re cube is the total, or the equivalent resistance of the network. So if we add all these and divide that with Ri, and multiply that with Vs, we can determine the voltage across that specific resistor. So here we've covered a couple of things. So the first one is we've seen how to determine the equivalent resistance. So for seriously connected resistors, the total resistance is always equal to the sum of resistors. So R equivalent, or the total resistance, will be the sum of Ri, where I starts from 1 up to n. And this is a summation sign. So the equivalent resistance will be the sum of the resistors. So it goes, this is R1 plus R2 plus R3. It goes like this until it reaches to the last one, Rn. So we simply add all the resistance of each component to determine the equivalent resistance. So, and this is true for series connection again. Don't forget that. So all these things are assuming that we have series. So this is a series connection. So if resistors are connected in series, their equivalent resistance will be simply the sum of the resistance of each component. And all these components have the same current. The current across each component, let's say this is I. So the current, they have the same current. So I will be the same. We do have the same current across each component. And we can also use this voltage division rule to determine the voltage across each component without solving for the current. Okay, so the equivalent resistance of any number of resistors connected in series is the sum of the individual resistance. So if we have any component, it will be simply the sum of all those resistors, and the voltage division will be simply the nth component divided by the sum of the resistance, which is the equivalent resistance, multiplied the source voltage will give us the voltage across each component. Now let's go to the other case, which is parallel connection. Now, what if resistors are connected in parallel? Then in this case, we do have similar analysis, but the way we determine the equivalent resistance will be different. And now in this case, current will not be the same unless they all have the same resistance. And instead of a voltage division, here we'll have current division rule. Now, if let's say, if two resistors are connected in parallel, they will have the same voltage. Now, for series connection, we said they will have the same current, but in this case, if resistors are connected in parallel, they always have the same voltage. If we have 100 resistors, each component will have the same voltage. So always, that's one thing we should remember. And the other thing is how to, let me just use this whiteboard. Now, how to differentiate between components that are connected in series and in parallel. So if resistors are connected in parallel, let's say this is R1, and let's say this is another resistor, R2. Now, for series connection, if you remember, we said that if we have two components, R1 and R2, we said that these two resistors are connected in series if and only if we connect only one terminal from each component. So they will have only one common point, and there's nothing, there's no any other component connected to that except these two resistors. So in this case, this is for series connection. But for parallel connection, each resistor has to be connected at their terminals, in both terminals. Now R1 is connected to R2 on the bottom as well as on the top. And then we'll have one common line that goes from here. We do have another common line that goes from here. Now, if you see, these two resistors are connected in parallel. Now, if current flows, let's say current flows through this wire like this. Let's say the current is I. Now, if current flows, this current will come, right? Now, at this junction, or at this node, current splits, right? So let's say this is I2, and let's say this is I1. Now the current splits. It's obvious that now I1 and I2 are not exactly the same. But in the case of, for the case of series connection, we said if this is I, the same current flows, so this is also I. So for series connection, they do have the same current. But for parallel connection, current will not be the same. The only thing that will be the same is voltage. If this is plus minus, and if the voltage across this one is V, this is also plus minus. The voltage across that will also be V. So they have the same voltage. That's the only thing. If I have multiple components, all those components will have the same voltage. Now, if we do have multiple resistors, let's say that we have, let me just add. So let me just add another resistor here. This is R3. Now we can see that R1, R2, and R3 are connected in parallel. So what I will do is I will just move only, I'll only move the line. So if you see, it's just a wire, so you can move. So R1, R2, and R3 are all connected in parallel. R1 and R3 are connected at this junction. R1 and R2 are connected at this junction. And R3 and R2 are also connected at this junction. All the three components are connected to the same junction at both ends. So therefore, all these three are connected in parallel. So now we have parallel connection. Now, if I add a fourth one, a fifth one, I can still continue. So I can continue. I can add like this. So I can say this is R4, this is R5. It can go like this. So all these components are in parallel. It's just like a ladder. So we have a ladder form. So all these components are connected in parallel. Now, let me change the color. So now the current through this one, let's say this is I2. The current through this one is I1. The current through this one is I3. The current through this one is I4. The current through this one is I5. Now there are 5 components, 5 different currents, unless all resistance are equal or they are identical. So if R1 is equal to R2, equal to R3, equal to R4, equal to R5. If that is true, then the current across each component will be the same. But other than that, they will have different values. But they all have the same voltage. But don't forget that. So this will be plus minus V. 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 So the voltage between R2, R3, R1, R2, R1, R3, R3, R4, R4, R5 is the same. So they all have the same voltage. So in parallel connection, we have same voltage. But for series connection, we have same current. So these are the two things we need we need to understand. And the last thing about this parallel connection is how to determine, let me just remove this, how to determine the equivalent resistance and how to apply the voltage division rule. So in order to determine the equivalent resistance or the total resistance of parallel connection, what we will do is we'll just take the sum of the inverse of each component. So our equivalent or the total resistance will be 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R4 plus 1 over R5. So we have 5 components. It goes like this. If this continues until, let's say, Rn, if I have n components and n of them are connected in parallel, then this summation also continues until it reaches 1 over Rn. So this is how we determine the equivalent resistance of parallel connection if we have a purely resistive component. If we only have resistors, and if all these resistors are connected in parallel, the equivalent resistance will be the sum of the inverse of each resistance. That's one thing. And the second thing is, if we want to find the current across each component, let's say I want to determine I1. So I1 will be 1 over R1 divided by 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R4 plus 1 over R5, because we have only 5 components. Well, if you see the denominator is, right, this is 1 over Req. So don't forget, times Is. So this is equal to 1 over R1, 1 over Req times Is. So the current division is given us 1 over R1 divided by 1 over Req times Is. So this is, if you flip this is Req over R1 times Is. So this is the current division rule. So if we simplify this, let me just, so if you simplify this, this is exactly, if I write the last one, so this is R equivalent over R1 times Is. So this is the current division rule. Now, if we want to determine the current across the second component, the third component, we follow the same approach. Let's say I want to find I for the I's component. So this will be R equivalent over Ri times Is. And that's it. So that is current. This is the current division rule. The current division rule. So just like we had for the voltage division rule, or for series connection, this will be the current division rule for parallel connection. Okay. So if we have 2 components, if we only have 2 resistors, R1 and R2, then the voltage division rule can be further simplified into this. So these are a very simplified expression for 2 components. If we only have 2 resistors, if we have multiple resistors, so the expression that I showed you earlier is a general one, but if we have only 2 resistors, the previous expression can also be simplified into this. So we can use this. So this is the current division rule that helps us to determine the current across each component. And we also say that equivalent resistance is can be determined by adding the inverse of the resistance of each component. So this 1 over Req, or the equivalent resistance, or the total resistance, is equal to 1 over R1 plus 1 over R2 till 1 over Rn when n is the last component. We do have also another term called conductance. G is for conductance, R is for resistance. Conductance is the inverse of resistance. So resistance is the ability to oppose the flow of charges, resistance, and conductance is the inverse of that. So we can use a current division rule using conductance. We've seen how to use resistance. It is IN is just 1 over R1 plus 1 over R1 plus 1 over R2 and something like that. We can substitute those 1 over R values with conductance. If we do that, we can also use this way. So we can use conductance or resistance to determine the current across each component. So in this lecture, we specifically focused on series and parallel connection of resistors and voltage and current division rules.